We probably won't pounds, and then next time we'll hope to at least finish that and talk about evolutionary aspects so that on Friday we can pass out the test. If we will, if possible, get through the grape and wine phenol discussion. If not, we may hold that over till after the take-home test. Now, I realize that skating through these kinds of compounds like we're doing is probably frustrating to a degree. It is to me as well. I find, perhaps more than you, I find this sort of thing rather fascinating, and there are, we could spend probably a half a day on each kind of compounds and talking about where and how they occur and what's fascinating about it, at least to me, if not to you as well. But rather than do that, I'll try to pick up a few of these things on the take-home test in the sense that I'll lead you to looking up a few things that I think are interesting. But along the way, I would like to point out a few. Now, on page 6 of your notes, we've got the section devoted to phenols with long aliphatic side chains and two important groups of compounds not listed that should be listed there and probably should be asterisked as important. We tend to forget them because they're biochemically important compounds and only fairly recently discovered. But the ubiquinones, which were known as coenzyme Q for a while during its period of discovery, I guess maybe still called that occasionally, is a series of benzoquinone derivatives with the basic ring structure like so, and then the isoprene-derived side chain from 6 to 10 units attached to the benzoquinone ring. And they are synthesized, as you would predict, from the isoprene type pathway. The plastoquinones are superficially quite similar, except methyl groups instead of methoxy groups and lacking a substituent in one position. The ubiquinones have been found in every living system looked at, except, the last I knew, gram-positive bacteria and blue-green algae. But animals, plants, and so forth, other than that, bacteria that have been looked at do contain them, and they are important respiratory chain participants in the electron transfer series of reactions. The plastoquinones are less widely distributed, being related to the chloroplasts and the green plant in somewhat the same way, but they also have the ubiquinones. So these should be mentioned. However, while we're talking about this group, and these might be added to your sheets, those that are listed on the sheets, if you'll run down the botanical sources, there are a couple of interesting things that you might not notice by yourself. For instance, the ginkgo or ginkgo, it's very hard to pronounce that correctly, but it's spelled G-I-N-K-G-O, and I believe comes from Japanese. I'm not certain of that. This ginkgo tree, you may know, is sometimes called the tree of heaven. It's grown in many yards and is a somewhat decorative tree. It's a very primitive coal-age type tree. It's been around for an awful long time in essentially unchanged botanical form. So that implies that some of these compounds are obviously very old botanical products, in the sense that the oldest type of tree does contain them. A second point to notice, and you might not know this, but under the observations it mentions that the Anacardiaceae, or the cashew family, is noted for this sort of compound. Well, the cashew family might not mean very much to you, and it didn't to me until I began this sort of study, but it includes not only Anacardium occidentale, which is the cashew, but it includes the mango, which is the tropical tree fruit that anybody that's been to the tropics knows and probably loves, or hates, as the case may be. A few people don't like it, but mostly people do. And it also includes one of our friendly plants of the Sierras, the poison oak, and the Midwestern poison ivy. The Rhus, R-H-U-S genus, include Rhus toxicodendron, and that's misspelled, dendron it should be, not denson on your notes. Toxicodendron is the one of the two. I believe that's the poison oak. No, that's the poison ivy, and I think Vernicifera must be the Japan lacquer tree. In any case, a rus species is used to make this beautiful lacquerware that you see from Japan and Oriental countries. Now often plastic, but the original at least was made by the sap from this tree, and the sap is just as toxic as the sap from the poison oak, and you can imagine the pain of the workers that work with it. But when smeared on properly, it will harden and dry to produce that beautiful, hard, polishable lacquer finish. A little sidelight on that that you may remember from the news a few years or so ago, when the late lamented president went to China. The visitation was generally received with great pomp and circumstance, and they'd gone to a lot of trouble of redecorating everything, and the only thing was that a number of the people began to get a sort of a donut-shaped irritation in their nether parts, and they couldn't figure out what was going on. And it turned out, after considerable investigation, that they'd repainted all the toilet seats with Japan lacquer, and it was too fresh, and they got the equivalent of poison ivy from the toilet seat. Whether that was revenge of an inscrutable Oriental type or whether it was accidental is a little hard to know at this time. In any case, not only is that kind of reaction found in those two cases, but it's also found in the cashew, in the sense of, I don't know how many of you know much about the cashew, but it grows as a funny-looking appendage on the end of what's called what we know as the nut, grows here, and this is called the cashew apple. And I've tried, and I lived in the tropics for a while, but I was never in the right place at the right time. I never have been able to taste a cashew apple, but they are eaten in any case. But this nut, so-called, is roasted in order to become the cashew nut of commerce, and it has a hull which contains this same sort of irritating oil, and it is roasted partly so that that oil will be removed and decomposed. If any, it isn't in the nut itself, but it might be contaminating from the hull. And that's part of the reason for the roasting, because in the heating process it decomposes to products that are no longer irritating. But then they have a fair amount of cashew oil from the hulls, and the nuts come from largely India and Madagascar, and they use this then in making plastics and what have you. And it's, for instance, occasionally found as a potting oil in transformers and that kind of thing. And an occasional electrical worker in Minnesota will come down with some strange skin eruption from working with electrical goods that have been made somewhere else and wonder what happened. But it comes from the cashew oil that was not properly decomposed to non-toxic products. And we could go on and on. You notice Semicarpus listed there. Semicarpus includes one plant, the species name which has escaped me right at the moment, but it's called the marking nut, and it was at least used in the Orient as chalk or as marking agent, and was frequently used to mark laundry, so that if you wanted to put a laundry mark on something, that it would survive the laundering process and you'd get the clothing right to the back to the right people. Then you'd put this on. Well, of course, as usual, they'd mark it in the back of the collar on shirts and so forth, and then you'd have a rash on the back of your neck from this marking nut. And it took an amazing long time before people found out what was causing it, and I suppose converted to inks that are not so much of a problem. So there's a whole host of interesting problems in this regard, and these tropical type plants have not been nearly as well identified and studied as might be. I have occasionally dreamed of the idea of getting Rockefeller to give me $1 million or two, and I could go down to the Amazon and build a nice fortified compound where I could run out and grab a few of these and then spend the rest of my life happily taking a look at all the strange compounds that occur in these tropical plants. Needless to say, it's not likely to happen, but I think there are days when I think that would be a great way to spend the rest of your life. The mango, for instance, is kind of related to the same thing. I don't know how many of you know the mango, but when the fruit develops, it's on a long peduncle and has kind of a pear or sometimes kidney-shaped shape. And it has a rather thick, tough skin, and one of the things that you'll learn, if you didn't already know it fairly soon, is that you shouldn't eat it out of hand. You shouldn't bite the peeling. You use a knife and peel it. It has a very hairy seed too, by the way, if you're not familiar with it, so you have to kind of chew off the meat from the seed. But that is, the wild varieties at least do. The commercial have been de-haired to some extent. But the point I want to make is, as you pick the fruit, there's a white milky sap that exudes from this stem, and you may see them in the market. They are in the market here occasionally. And if you look closely, you'll often see little bright shiny patches on the skin. Well, those bright shiny patches are from this same milky sap that's like the Japan lacquer sap, except it's not so likely to turn black. And it does oxidize and harden to make a paint-like surface wherever it gets on the fruit. But the point being, again, that's irritant and poison ivy-like, and so that if you eat it out of hand, you're apt to get a breaking out around the mouth that's poison ivy, and if you've ever had poison oak on the leg, you can imagine how it'd be on the face. It's not that much, not that pleasant. So it does pay to peel. And the peeling has a little bit, but very little, and the flesh has none. So perfectly safe to eat, but can cause dermatitis if you aren't so careful about the sap getting on you as you pick the fruit, or from the fruit skin into your mouth or wherever. Well, that's an example of the kind of sidelight that would obviously be fun to talk about, but we won't allow ourselves to be distracted too often. Just leafing through from here on, we've talked a little bit about polycyclic substances, and say, for instance, on page 10, you notice Hypericin about the middle of page 10, a very complicated looking structure, but it can be visualized as two anthraquinones cross-linked, but it sort of reminds me of, I had a joker-type professor once who liked to put things like this on the board. One day he came in and wrote, I don't know exactly how many rings, but a whole bunch of rings like so, and he put on a couple of methyl groups and asked us if we could name this. And of course we weren't able to name it, so after a certain amount of time he said, well, that's dimethyl chicken wire. So Hypericin is almost as bad as dimethyl chicken wire if you take a look at it. Anyway, Hypericin we've mentioned, I think, if not briefly again, one of these interesting sidelights. It occurs in St. John's wort, which is one of these, Hypericum perforatum, I believe it is. In any case, St. John's wort, or wort for the beer people, is a weed that's been introduced from Europe into the New World, but is rather prevalent in the foothills of the Sierras these days. And it has caused a certain amount of trouble because it's not a plant that animals eat readily, but if they have nothing much else to eat, they will eat it. And I think I've mentioned that if they do eat it, then the sun will affect the animal in the white-skinned areas, so that if you have a black and white spotted cow, it'll have an edema and a sunburnish type reaction, but it's such a severe reaction in the white areas that it may kill the animal. And in fact, a white cow is likely to die from eating this compound, Hypericin, and then being exposed to sun. And neither alone will kill them. So that if you have such animals, then if you put them in a dark barn until they've had a chance to get this out of their system, they will survive. And it's a very fascinating, further fascinating story. For instance, if the animal has been affected by eating St. John's wort, one way you can diagnose it is you shine a UV light into their mouth, and if their mouth looks red, fluoresces red, then that shows the Hypericin in the skin, and shows that that's probably what's the matter with them. You can imagine going into the barn with a UV light and all the cows that have red mouths being the ones that you would do something about, at least put them in the dark. Another point of somewhat of an interest is that if the animals become chilled, like for instance if you're driving them through a stream, they have to ford a stream and the water's cold, having eaten Hypericin, they're apt to go into convulsions and drown from some effect of the chilling, so that there is an interaction with the nervous system over and above the skin effects and the light sensitization effects. So a lot of these compounds have very interesting stories of that type. Well, I won't stop again, I don't think, for the unusual things, but let's spend a little time on the usual or more important things. Page 12 discusses or mentions the depsides and related esters. Now, depsides, strictly speaking, are esters between two phenolic acids, or at least a phenol and a phenolic acid. These depsides occur in lichen and mold products. By and large, if you stick to that strict definition, they're rare in higher plants. Meta-digalic acid is, in fact, a depside, and meta-digalic acid you'll see on bottles. You'll find bottles labeled meta-digalic acid when they aren't. But the compound we're talking about is gallic acid esterified on one of the meta-OHs of another gallic acid. So two gallic acids, one esterified to one of the meta-OHs, becomes meta-digalic acid. And that is a compound that you can isolate from tannic acid and is a compound that you can synthesize, but not one that's easy to come by. And I don't know why, but for some reason or other, a lot of old bottles of tannic acid are improperly labeled meta-digalic because they are just tannic acid, and they contain a fair amount of meta-digalic, but it's by no means pure, and not even the major constituent in many cases. Well, with that one exception, there are relatively few true depsides in higher plants, but there are a number of phenolic acid esters that are important, and perhaps it's not quite fair to group them with the depsides, but it seemed like the best place to discuss them. And the most interesting one is chlorogenic acid, most interesting in the sense that it's extremely widespread. Nearly every plant has chlorogenic acid, and the structure is given on page 13. And notice that the quinic acid, which is the caffeic acid, is esterified to quinic acid. And for chlorogenic acid itself, it's esterified to the 3 position of the quinic acid. And the quinic acid is drawn in the, it's a allocyclic carbon compound, and is drawn in the boat form. Now let's make a little jog so you can see there's a carbon there. So this would be, or rather the chair form, excuse me, the chair form of the quinic acid. And quinic acid has an OH group here, and a carboxyl group, and an OH group on the carbon number 1. And as drawn, we're going around in this direction. And the 3 position is the one that the caffeic acid is esterified to. Now the OH group in the 5 position is axial, and the ones in the 3 and 4 position are equatorial. Now, if you're not familiar with that nomenclature, you can visualize it as a wheel. And so anything that comes off of the ring in this direction would be axial, and anything that comes off radially would be equatorial. So it would be reasonable that the equatorial OH here in the 3 position would be one most readily esterified, in that it is sort of oriented away from the ring and would be in the hydrogen then. Whatever else is on that carbon has to be axial. So if one is equatorial, the other has to be, one group on a carbon is equatorial, the other has to be axial. So in this case, this is axial, and the hydrogen would be equatorial. And in this case, the OH is equatorial, and here as well. Well, that has some bearing in knowing where or why it's reasonable that the 3 position would apparently be the one most readily esterified, and in nature chlorogenic acid is more prevalent. However, neochlorogenic acid, which is 5-caffeoylquinic acid, so it is esterified on what would normally be an axial OH group. This is known in nature. It's called neochlorogenic acid. BAN 510, and as far as I know, it still doesn't have a better name than that, because it would generally be called now 4-caffeoylquinic acid, would be the third member, the third position isomer possible. You will run across the term isochlorogenic acid in the literature, but it's been now shown that isochlorogenic acid is a misnomer. It was a mixture of di-caffeoylquinic acids, and the mixture is fairly complicated in that 3,4, 3,5, and 4,5, all possible di-caffeoylquinic acid isomers apparently occurred in the mixture. Now this sort of isomerization can be important. For example, if we have free quinic acid, the carboxyl group in this position can form a lactone with the OH in this position. But if that occurs, obviously, this which is axial ordinarily, has to bend around to reach this, and the OH would have to become axial. If that happens, then it means the ring has to go through a rearrangement so that it probably is then in the boat form. At least it has to be so that the OH becomes axial or more nearly oriented to the OH group. So it is possible to produce the internal ester from quinic acid. Now we're talking about quinic acid even though it's not a phenol, because it occurs rarely in appreciable amounts free. As we, I think, mentioned already, it does occur in the apple as a high concentration, but very few other places, and mostly it's found as a part of chlorogenic acid. It's a very polar compound. Even with the ester group on one OH, there are still 3 OH groups left, which makes it very water soluble, and the carboxyl too, which makes it quite polar and quite water soluble. So the caffeic acid unit by itself is moderately water soluble, and then you add to it the almost equivalent of a sugar in terms of polarity, then you have a rather water soluble compound. And this becomes important because it appears that the chlorogenic acid type molecules are about the only kind of molecules that are readily translocated in higher plants. So most phenols are not translocated, and the evidence is that one of the way that a phenol may be translocated is by a chlorogenic. So either a phenol that's found in place in a given cell is manufactured from sugar and other components at that point, or if it's translocated in as a phenol, it would be in the form of chlorogenic acid, apparently. At least it's one of the best documented examples of such translocation. Another point of some interest, I hope, is that the OH group in the 5 position is, no, wait a second here. Oh, the hydrogen. The hydrogen in the 5 position is the only equatorial hydrogen. And in oxidation of quinic and shikimic, etc., to the 5-dehydro type of compound, where this OH becomes a keto group, the 5-dehydro quinic acid occurs in the 5 position because the hydrogen is equatorial and is therefore more readily oxidized off. So you might wonder, the apparent equivalence of the OHs in the other positions might cause you to say, well, why is it always 5-dehydro? Well, it may be enzyme specificity, of course, which a biochemist can always fall back on, and if you can't explain it by organic chemistry, you can always say, well, the enzyme makes it do it that way. The devil told me to, as Flip Wilson would say. But on the other hand, in this case, there is good chemistry that would explain why it is the 5-dehydro that would be the most readily produced oxidized form. There are a number of similar compounds in the chlorogenic acid family, from shikimic derivatives and from instead of quinic, and vice versa with paracoumaric acid instead of caffeic, and even some with ferulic and other of the cinnamic acid sorts. But by all odds, the most important are the ones that we've mentioned. Then I think we'll just skip over the phenolic alcohols. Again, I wouldn't mind to have time. For instance, tyrosol is the fusel oil equivalent from tyrosine, and is produced by yeast, is found in wine, and so forth, but we won't take time for it. Phenolic aldehydes are important in some cases. Vanillin is a very important flavor compound, and syringe aldehyde and synapaldehyde occur in oak heartwood, and therefore in wine by extraction from barrels. But again, these are personal interests that are not terribly important from a general occurrence viewpoint. The acetophenones are a fairly unimportant group from a wine viewpoint at least, and so are the benzophenones, although some of them can be very important for other reasons. On page 18, among the benzophenones, you'll see cotoin mentioned, and cotoin is, at least according to some measurements, the most toxic phenol that we know. So that even though it's a fairly simple thing, it's pretty toxic, and at least as measured, it hasn't been measured in higher animals very much, but in terms of the minimum lethal dose for cold-blooded animals like frogs, it only takes a few, well, a milligram or so to kill a frog, and that's among the most toxic on an acute basis of any known phenol.
Where is that?
Page 18, cotoin, near the top. It's a fluoroglucinol derivative with a benzophenone side chain. And it occurs in coto bark, which was one time used for medicine, and you may be interested that that's a Rhamnus species, and you realize that Rhamnus is a genus in Rhamnaceae, and that's the next family to Vitaceae and the Rhamnales. So when you see Rhamnose and a number of these things related to the Rhamnus species, you should realize that that's pretty close to grapes, and when we see a very poisonous compound in that area, and the anthraquinones in the laxative group also come in this same type, we're rather glad that even though they're closely botanically related, that the grape learned how to avoid, or didn't learn how to produce, whichever, some of these strange compounds. The xanthones are a fairly limited but unusual group. I might point out mangiferin, or mangiferin, however you prefer to pronounce it. This compound is related to some that are found as dyes, and it happens that if mangiferin, as it occurs in the Mangifera indica bark, which is Indian mango, the Indian mango leaves also contain it, and what they used to do in India was they'd pen up a cow and feed her on mango leaves and then catch the urine, and the urine would contain a glycosided version of mangiferin that the cow, or bucuronic acid derivative that the cow produced, made the cow sick, in other words, and had to detoxify all this mangiferin from the leaves, but it converted it to a more water-soluble derivative, and then the cow urine was used to produce yellow textiles. So they've outlawed this now, and there's a cruelty to animals sort of thing. But if you bought a Madras shirt 10 years ago, chances are if it had any yellow on it, it was because some poor cow was giving her all for your yellow shirt. On page 19, the group of still beans is discussed or started, and notice pinosylvan is mentioned. Pinosylvan is an example, and many of the still beans which are two benzene rings with two carbon unsaturation between. So they're not C6, C3, C6 compounds, but rather C6, C2, C6 compounds, and they're found widely in the pines and related plants, not very widely in other plants, although as you see there are a few other examples like hydrangea that does contain similar compounds. These are of interest for another reason, and they do represent a group of tannins of a very limited distribution, but tannins by and large are either gallic acid derivatives or catechin type derivatives. and we'll talk more about that shortly, but there is a third group that the tannins apparently are made from still bean, and this occurs in certain pines. The complex fluoroglucinol derivatives mentioned on pages 20 and 21 would be considered curiosities, and to some degree they still are, if it weren't for beer. And of course humulone and lupulone occur in hops and are part of the reason hops are used. These compounds, when properly treated with heat and in the brewing process, contribute to the bitter flavor produced from hops. And they're also probably the original reason for use of hops. They're somewhat antibiotic, so that when you were making bread, they used to use hops in making bread as well as with beer. And they would be fairly good antibiotics against things other than yeast, so that it would prevent you getting growth of certain bacteria and so on that otherwise might spoil your beer or your bread. And then we like the bitterness and the aromatic characters that are not phenolic from hops, and therefore beer is still made with hops. Now it kind of bothers me, and I hate to mention this too loudly for fear I like beer, but it does bother me that the most closely related compounds of this series are things like albaspidin and phylicin and flavonoids acid that you'll see near the bottom of page 21, which are fern constituents. And while they've been used as drugs for a long time, they're probably still the best drug against tapeworms. So if you have a tapeworm and want to get rid of it, you take a dried ground fern preparation is the best thing that does the job. Nevertheless, these compounds are pretty toxic, and there have been incidences where a person got a hold of the tapeworm medicine and took too much of it thinking it was something else and died from it. In other words, they are pretty toxic. And considering the gallons of beer consumed over a person's lifetime, it might be well worth doing a more thorough study as to whether or not these beer constituents are something we should worry about. Notice that on page 20, the phenolic acid, which also comes from a fern derivative, is drawn as a triketo derivative. And it must be a triketo derivative because you notice it's dimethyl substituted. So in other words, it cannot enolize to the fluoroglucinol derivative, and yet demethylated, it would automatically isomerize to the fluoroglucinol derivative, and therefore it's fair to consider it as a phenol derivative, or a phenol relative at least. Now the lignans, which are discussed on page 22, are an interesting group of compounds, and they're interesting mainly because they have analogies to lignin. However, these analogies must not be taken too far. The analogies are that the lignans are commonly made and biosynthetically made from 2 units of cinnamic acid or 2 shikimic acid derived rings. But the C6, C3 units that are polymerized to make the dimer are interestingly nearly always the same, so that you get a dimer of like units, even though sometimes in the same plant you may have a different lignan which is made from a different cinnamic acid derivative. What this means we don't quite know, but it does suggest that the 2 units are somehow sorted out, or maybe never escape the enzyme where they're formed until they're converted to the dimer. Another point that's considerably of interest is that some of these compounds, particularly nor-dihydroguaretic acid, which is the first one on the list, is used as an antioxidant in fats. So lard is treated with what may be called NDGA, and NDGA is nor-dihydroguaretic acid, and NDGA is obtained from a mesquite-like plant in the southwest and then used as this antioxidant in lard, along with other synthetic phenols such as propylgallate and other such compounds. So in other words, it does oxidize readily, and in the course of its oxidation it prevents the fat oxidation that otherwise would occur, so you avoid oxidative rancidity in the lard, and since it is a food additive, we've been eating it for a long time, and by and large it appears to be innocuous, at least at reasonable dosages. And the other phenols that are used similar, but it illustrates a use of a readily oxidizable phenol. Another point of considerable interest to me is that when you have a dimeric lignin, if it's possible to be optically active, it usually is, so that the asymmetric carbons, which are marked with asterisks in the appropriate compounds, are put together in an asymmetric way. Now, in lignin, by and large, the lignin units which look the same as these are not optically active. So it would appear that lignin is made by enzymatically non-specific reactions, probably even just by what might be called test tube chemistry rather than by enzymatic control, whereas the lignans, on the other hand, are made by enzymatic control and are optically active. And so it suggests that perhaps we shouldn't believe too much about lignin structure from studying lignans. Further point before we leave the lignans is some of them are quite interesting from a physiological activity viewpoint, and podophyllitoxin, which is given in the middle of the page, is this Mayapple root toxin that I think I mentioned once before, is very toxic and therefore is no longer used, but at one time it was used for a potent laxative and also as it was investigated as an anti-cancer drug. So far as I know, the only drug use it still has is referred to somewhat cryptically, and I haven't been able to find much more about it, but it says that it's used to remove certain types of venereal warts. Now, I'm not sure what venereal wart condition would be, but I'm glad I haven't seen any pictures of it. And it apparently can be applied topically in that case and is sufficiently toxic that it will penetrate the skin and kill the growing centers of these warts, and then you'll revert to normal, presumably. Again, a rather fascinating compound. Notice that Tumeric Spice, which is from the ginger family, contains curcumin, at least as a coloring agent. I'm not so sure whether it contributes to the flavor, but it is part of the reason that turmeric is yellow, or the reason turmeric is yellow. The coumarins are a very, very large group. They're found particularly frequently in the legumes, but not confined to the legumes, and several of them you'll notice are asterisk, and the asterisk can mean that they're common in occurrence, and that's the main thing it means in this case. Can also mean that they're important for other reasons. We might diverge briefly to talk about pronunciation. I have my own theories about how certain things ought to be pronounced, and you can say I'm right or say I'm wrong as you see fit. But for instance, this compound can be pronounced and is pronounced in more than one way. You'll find it pronounced scopolitan with the emphasis on the pol, but I prefer to pronounce it scopolitan with the emphasis on the E. Now you could call it scopolitan, I suppose, and do that too, but the point is it becomes hard to understand what you're saying, and it's not so important with this compound maybe, but the eton ending sort of brings it to your attention that it's a compound of a natural sort. The IN ending basically derives from meaning it was in something. So the IN ending suggests a natural product, and often the first part of the name suggests what plant it was in. Offhand, I don't remember what scopolitan comes from. It's probably a genus name in the tobacco family, but in any case, scopolitan is the way I prefer to pronounce that, and that would make daphneton, fraxiton, esculeton all sound more or less alike. There is a further reason I might as well give while I'm right here. There is a flavonol, quercetin, and it becomes important there to call it quercetin, because if you call it quercetin, as people do, it suggests it comes from oak, which is where it did come from. But quercetin you have a hard time hearing, and there is another compound, quercitrin, which is a glycoside. So that if you say quercetin, you can tell the difference from quercitrin without any trouble, whereas if you say quercetin and quercitrin, you have to listen mighty hard to know the difference. So for that kind of reason, I would prefer to pronounce it this way. And as I say, the dictionary says I'm wrong in the case of scopoletin. They call it scopolitan, but I don't think a dictionary should be telling chemists how to say things. The chemists ought to be telling the dictionary. And so I'm going to hold my own against Webster in that particular case. The Furo Coumarins are an important subgroup, and again, they tend to be found in legumes. We've mentioned isobergaptine and bergaptine. It was pointed out to me that in the earlier structure, the isobergaptine, I believe it was, didn't have the oxygen in the heterocyclic ring, so if you get troubled by that, look back here. And while we're on the point, on page 25 near the bottom, isobergaptine, that structure isn't very clearly written. That should be a furano ring, so it's a four carbon or 5-membered ring in the upper left corner, so that it is not a 5-member. You might want to clear it. It was written correctly, but it was slipped so that it doesn't look too clear cut. And all these derivatives have the furane type ring attached to the normal coumarin, the coumarin of course being derived from cinnamic acid. The isocoumarins are mentioned and they involve a substitution so that it is not an obvious cinnamic acid derivative, and they are not always clearly produced from the shikimic acid pathway. So coumarins don't necessarily arrive only from the shikimate pathway, but they seem nearly always, and all the common ones, from that pathway. The chromines and chromans, other than flavonoids, are a rather special and not terribly important group, except for the tocopherols. And the tocopherols, which are the vitamin Z, are chromans, or at least so can be so considered. And except for those, then we aren't too concerned with this group. Brazilin on page 27 with the tocopherols and vitamin E is an interesting compound in the sense that the word comes from, the word brazier, not what you're thinking, but the place where you charcoal broil things. The braz in that case comes from a word meaning live coals. And so Brazilin gets its name from a wood that has a bright red dye in it and is used to dye cloth, or was at least. And this bright red dye is Brazilin. And in fact, the country Brazil got its name because of the export of this bright red wood from Brazil. So that's a kind of an interesting sidelight, I think, too. The vitamins E are very important as natural antioxidants and participants in various reactions, such as prevention of damage from free radicals, so that smog damage, you've probably read, if you take a lot of vitamin E, you're a little more resistant to smog involvement, apparently, and may not get old quite as fast. And if you want to know more about that, you should talk to Dr. Tapple in food science. I don't claim to know a great deal about the field, but I do take a little vitamin E now and again because it sounds like a pretty good idea. For other reasons too, perhaps. The chromones and chromanones are again an interesting but not terribly important group with a couple of exceptions. I've listed rotenone in the group on page 28, and you know that rotenone is an insecticidal compound. Perhaps it should be called an isoflavone. Certainly biosynthetically it is an isoflavone derivative, but it also would fit under this class of chromanone. It, of course, is a rather rare occurrence. It's known in a couple of tropical area, 3 genera of the Leguminosae, and again suggesting that the legume plants are a particularly important source of some of these rather unusual types of isoflavones and coumarins. In that same group, there is a group of Kellen, for example, which Kellen is a constituent of a Egyptian plant, Ami visnaga, and therefore visnagan is another compound in the series. And these compounds are involved as part of the tranquilizer family related to reserpine and although reciprine is something else. But these, in native medicine, the plants that produce these compounds were used together as tranquilizers and various types of blood pressure lowering, hypertension correction type of treatments. So they have some interesting importance physiologically too, or drug uses. Well, this brings us to the flavonoids, and the flavonoids are probably as numerous as all the others put together, or certainly more common, and except for the cinnamates are the most important group of naturally occurring common plant phenols. And I could spend several lectures on them, but I would rather not. We'll just briefly talk about the groups and the important compounds. For instance, the first group listed is the flavan-3-ols, and that would be the Catechin Group. And just as we mentioned in the case of quinic acid, there are some important chemical facts that relate to apparently trivial findings. So that if we have catechin, making sure I get my OHs in the right position, we have at the 2 position and the 3 position asymmetric centers. In other words, a carbon with 3 different groups attached to it. So that's a optically active carbon and an asymmetric center. And the 3 position is the same thing. And the arrangement in D-catechin is like this, where the hydrogen and the phenyl group are behind the plane of the blackboard, and the OH and the hydrogen are in front of the plane of the blackboard, and the heterocyclic ring is in the plane of the blackboard. So we have the 2 asymmetric centers, and D-catechin and L-epicatechin, or plus catechin and minus epicatechin in terms of optical rotation, are the 2 naturally occurring forms. But there are the other 2 forms of L, or minus catechin, and D, or plus epicatechin, which do not occur in nature, but can be produced rather easily as artifacts from the naturally occurring forms. And just without taking too much time, I would like to say that this sort of apparently minor chemical difference can have important bearing on reactivity. For instance, D-catechin, which is the one we've drawn here, has the OH group and the hydrogen in the 2 position on opposite sides, or rather on the same side, excuse me. And therefore it cannot be readily dehydrated, whereas the epicatechin, which has the reverse, with the hydrogen here behind the board and then the OH group here in front of the board, and therefore the OH and the hydrogen are trans to each other. Now, dehydration is a trans-elimination reaction, so it's possible to eliminate the elements of water and produce a flavine from epicatechin very easily, and it's practically impossible. In fact, it is impossible to produce a normal 2,3-flavine from D-catechin. And that also has bearing in the oxidation, because you realize if you can produce a double bond here, then that's in conjugation with the bonding of the B ring, so that the ready oxidation of epicatechin compared to D-catechin is somewhat explainable. So apparently minor changes in the stereochemistry can make a big change in the actual behavior of the compound. Are we going to go ahead with our take-home test to be distributed Friday and not meet Monday, or did you want to veto that?